So this is chapter 10, continuing on with what we were just discussing with the ideal gas law and deriving what we call a relationship between the velocity of the gas and essentially its mass. So what we derived essentially was something called the root mean squared speed. So RMS. Your book uses a U, which is very confusing. I think we should just use a V, but that's what you see in the book for this. So it is the velocity of the gas is the square root of 3 times R times T over the molar mass. Now the key to this is you have to have the molar mass in kilojoules per mole, and I will show you why. And R has to be the 8.314 joules per mole Kelvin. And I will show you how that's all related. So we did this before in a previous discussion, but we know that a joule coming from Einstein's equation is E is equal to mc squared. So we know that a joule of energy is equal to kilograms times meters over seconds squared. So if I plug in units for my R, my T, and my molar mass here, if I have my R as joules per mole Kelvin, and my temperature is in Kelvin, and my molar mass is in kilograms, per mole, what happens is the mole cancels the mole, the Kelvin cancels the Kelvin. So how do I cancel out the joule with the kilogram? So I have to go back to this equation. So if I plug in joule as kilogram times meters over second squared, so I take this and plug that in here for my joule, and I have kilogram on the bottom. Well, kilogram cancels kilogram, and the square root will cancel out the square, and so what you will be left with is meters over seconds, which is your velocity, okay, your speed essentially. And again, we don't care about direction, so speed, velocity, at least in chemistry, is kind of interchangeable. And again, your book uses the U RMS. I don't care if you use that. So we're going to use that in some calculations. But before we get to that, we're going to talk about the speed of these particles and what we could see in terms of their relationship. So what we have in your notes here is something called the Maxwell-Boltzmann distribution. So this is going to give you some background into that Boltzmann concept that I showed you before. So for this discussion here, we have this graph, and we have the number of molecules versus the speed. So what you could do is highlight this first curve here. Okay, this curve here is 100 Kelvin. Okay, so it's a gas at that temperature. And then if you want to highlight or kind of focus on this curve here, this is at 700. Okay, so these curves themselves are called the Maxwell-Boltzmann distribution. And what they're trying to show is essentially, these are all, this is showing all of the gas particles in a container. So realize gases in a container are moving randomly, and they're all going to have different speed. But what this shows you is what we call the distribution of all of those speeds. So you might have something very slow versus something very fast, but at the top of each one of these curves is essentially your average. Okay, so when we take an average temperature and average speed, you're kind of doing that midpoint of that distribution. So remember that temperature is going to be proportional to speed. So the higher the temperature goes, you will see that the higher the average speed is going to be, okay? And realize that you have a larger distribution of speeds at 700 Kelvin, so it spreads out much further than you do at the lower temperature like you see with the 100. Okay, now realize that if I were to take the area underneath both of these curves, I would have the same number of particles. Okay, same number of molecules of gas. The only difference is in a higher temperature, I have a larger distribution. So I have a much larger span of speeds than I do at a lower concentration. okay? So this is, again, one gas only, okay? But we could also look at multiple different kinds of gases. So we are assuming in this next graph that everything is at the same temperature. Everything is at the same temperature. So I have oxygen, nitrogen, water, helium, and hydrogen. And again, these are all Boltzmann distributions. So it's, again, fraction of molecules versus molecular speed, and it's showing you meters per second for this. So if I look at this and they're all at the same temperature, it's telling me that the hydrogen gas here, okay, has a much larger distribution than, say, the oxygen gas, okay? And I will see that their speed, okay, their average speed is going to be very different, okay? Now, if they're both at the same temperature, so what is that telling us about the relationship between the hydrogen and the oxygen? If they're at the same temperature, the smaller molar mass, okay, of hydrogen versus the larger molar mass of oxygen, I have a much wider distribution with the hydrogen versus the oxygen because this is going to have a higher speed because of the mass. Okay, so the smaller it is, the higher the speed's going to be, average-wise. So again, oxygen is a molar mass of about 32, hydrogen is 2. So you will see that their speed is going to be dependent on their mass, okay? And that's what that equation is trying to show you, okay? So speed is proportional to that mass. How big is your molecule of gas going to be? So let's try these two problems and show you how to use the math calculations and mistakes that sometimes you make. So calculate the average speed of the hydrogen molecule in meters per second at 0 degrees Celsius and take it up to 3 sig figs. I got nothing to hold on to for sig figs, so let's just do 3 sig figs. Calculate the average kinetic energy of a hydrogen molecule at 0 degrees Celsius. So please understand this is looking at molecule. I'm going to pause the video and then you can see the answer. So calculate the average speed of a hydrogen molecule in meters per second at 0 degrees Celsius. So again, the velocity or speed of the hydrogen molecule is 3 RT over the molar mass. So I'm going to take 3 times 8.314 joules per mole Kelvin times 273 in Kelvin. And then please see if you made the mistake, 0.002 kilograms per mole. So it's not 2, it's going to be 0.002 kilograms per mole. Otherwise, it will not work. So you get about 1,850 meters per second for that hydrogen molecule, even at 0 degrees Celsius. Okay. And then the second one, I wanted you to see something according to molecule. So this one is the average 3/2 kb times T. So kb being the Boltzmann constant that I talked about, and now that we've talked about it, it might make a little bit more sense. So 3/2, and again, if you don't remember that number, just take the R, which is 8.314, and divide it by Avogadro's number, and then multiply it by the temperature. So you get about 5.65 times 10 to the negative 21st joules per joule molecules as your answer, which makes sense because, again, we're talking about one hydrogen molecule, so it's going to be a small number. So again, keep in mind with Boltzmann distribution, just the relationship between mass and how quickly that particle is going to go. So we kind of alluded to that a little bit in Graham's law as well.